So yesterday we found that systems kind of had a small part in our decomposition of fractions. Today we're going to go back directly to systems and talk about some nonlinear system solutions. Before we do that, let's just quickly go over a linear system. So if I have a linear system, I know that basically I have two lines intersecting at a single point, or two parallel lines, or a line that overlaps itself. And I can have three different solutions. Nonlinear systems are going to be something like parabolas and lines, circles, and maybe ellipses, etc., etc. And we're going to find the intersections of those. We know that our first method of solution was always substitution. So if I wanted to, I could take and say, well, I know that 2 over 3x plus 5 would be equal to negative 5x plus 8. Go ahead and multiply. I'd multiply all the sides by 3 to start with, just to get rid of fractions. So I'd have 2x plus 15 is equal to negative 15x plus 24. 17x would equal a total of 9, and then x equals 9 over 17. Once I know that x is 9 over 17, substitute back in, so y is equal to 2/3 times 9/17 plus 5, and y will equal 91 over 17. Nonlinear systems mean, once again, I'll have something like this where I have, this is a parabola, and this is a linear function. I know that parabola is going to be opening upwards. Linear function will have some kind of positive slope, probably looks something like this. But we confirm that by checking out what our solutions are. Again, on this problem I have a couple of options. I can take and add these up because my y's will reduce out, or I can take and use a direct substitution. Doesn't really matter. I'm just going to use substitution. I know y is equal to x squared plus 3. So therefore, if that's the case, I have 3x minus x squared plus 3 is equal to negative 1. That's x, or 3x minus x squared minus 3 equals negative 1. Set the side equal to 0. Get x squared minus 3x plus 2 is equal to 0. I get x minus 2, x minus 1 as solutions. Therefore, I know x is equal to 1 and x is equal to 2, which means I'm going to have two solutions, much like my picture here. Plug back in to find my y, and I can do that right here. I know that 1 squared plus 3 is 4, and 2 squared plus 3 is 7. So those were my two intersections would be. So in this problem, you'll notice we have a hyperbola and an ellipse, and I could once again take and use a substitution, but I think I'm just going to take and multiply by 2 in this case, giving me 4x squared minus 2y squared equals negative 2. Add up 5x squared, y squareds go away, equal to 20. X squared is equal to 4. So x equals plus and minus 2. So in that case, once again, I have two solutions. There's a 2 here, there's a negative 2 here, and then when I plug this back in, I'll get 4 plus 2y squared equals 22. Take and bring that over, that gives me 18 over 2 is equal to y squared. So you'll notice now, y squared is equal to 9. I have two answers for y. Y is equal to plus or minus 3. So I really have 2, 3, and 2, negative 3. And then when I plug negative 2 in, because I'm taking and squaring that value in the x squared function, I get the same two values. So I'm going to have 3 and negative 3 again. And this makes some sense because if I have an ellipse, and a hyperbola that are symmetric, you'll see that if they're centered along the same point, then I'll have those 4 symmetric solutions. Last, it looks like I've got a circle and an ellipse, probably going to have 4 solutions on this as well. Multiply in this case much like I did in the last problem. Let's go -3. So I get -3x squared minus 3y squared equals -21. Giving me x squared is equal to, this one's a little nastier, 3. So x equals plus or minus √3. So √3 and -√3. Plug back in to find y. I know that x is √3. When I square that, I get 3 plus y squared is equal to 7. I get the same thing if I plug a -√3 in. Y squared is equal to 4. So y equals plus and minus 2. And that's going to happen similarly in both. There's my +2. There's my -2. +2. And -2. Makes sense. Circle, ellipse, something like that. Centered at the same point, therefore symmetric solutions.